Hello everyone, my name is Kathan and today we will be discussing the problem collecting numbers from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. You are given an array that contains each number between 1 and n exactly once. So we have an array which has numbers between 1, 2, 3, so on till n exactly once. Our task is to collect the numbers from 1 to n in increasing order. You have to collect numbers like 1, 2, 3, so on in increasing order. On each round, you will go through the array from left to right and collect as many numbers as possible. What will be the number of rounds? So in a round, you go from start to end or left to right and try to collect numbers like 1, 2, 3, so on. But let's say you collect 1, 2, 3 and you don't find 4 here. Then you'll again start 4, 5, 6, so on and so forth. So we go from left to right and collect as many numbers as possible. What will be the total number of rounds? Right. So in a way, when you go from left to right, you cannot go back. Right. So let's see the input here. The input is simply the array itself here, right? So you can see first integer n, which describes that we have elements from 1 to n, and the next line has n integers x1, x2, so on to xn, and of course these numbers are in a range 1 to n, like in which every number between 1 to n is present exactly once. Fine. And output you have to print one integer, the number of rounds. And constraints here you can see that n can be as high as 10 power 5. So we'll talk about constraints in a bit, but here you can see example test case. So n is 5, so that means you'll have numbers from 1 to 5 exactly once in the array. You can see. Now what do you have to print? You have to collect the numbers. You have to collect the numbers like 1, 2, 1, 2, 3, 4, 5. Right? So how many rounds will be there here? First you'll collect 1. Then you'll collect 2, 3. Then you'll collect 4, 5. So you have to print 3 rounds. Don't worry, we'll see this test case again on the iPad. So that's about the question. We have an array of numbers from 1 to n and we have to collect them in order left to right, and you have to tell me how many number of rounds will be there. In a round you go from left to right. Fine. First things first, let's talk about constraints here. So n, which actually describes the array, and the number of elements can be as high as order of 10 power 5. So what does it suggest? That you can actually come up with order of n log n solution, or order of n solution, or maybe better than that, why not order of n square? Because see, if you have an order of n square solution, then total number of operations that will be consumed will be 10 power 5 into 10 power 5, which will be 10 power 10. Now 1 second time, in 1 second time limit, you cannot do 10 power 10 operations. You cannot do more than 10 power 8 operations. And 1 second is the time limit for this question. So order of n square is out. So you try to give me n log n, or maybe better than that. So with constraints clear, let's look at one example test case to solidify our understanding of the question. So I'll take the same example on the website. N was 5. We had numbers. So we'll have numbers from 1 to 5 exactly once in the array. So 4, 2, 1, 5, 3. Now the way a round works is we go from left to right and collect numbers in order. In the end, we want to collect numbers from 1, 2, 3, so on, n minus 1 till n. Right? So we want to collect numbers in order. Right. So we go from left to right, and like we want to collect the first number, which is 1. So we'll collect in first round the number 1. Then I look for 2, but I won't find 2. So fine. So one round is over. In one round we go from left to right, collecting numbers in order. Right. Fine. So we just found 1 in the first round. Then in the next round I again start. So I'm looking for 2 right. Right. So then I find 2. Okay. So maybe I'll use different color here. I find 2. Then I'll find 3. So in the second round I found 2, 3. Okay. And now there will be third round starting. In third round, first I'll find 4, then I'll find 5. So in the first round I found 1, then I'm looking for 2, but in the first round will be over and I won't be able to find 2, right? And then in the next round I'll find 2, then I'll find 3, right? And now I've reached the end of the array. So I moved left to right and I've reached the end of the array. Okay, next round. So in the next round I'm looking for 4, so I found 4 here. Then I'm looking for 5. Yeah, I found 5 here, and we have got all the elements. So what are total number of rounds here? 3. Right. So I guess the question is clear. Let's see how can we approach this question. Let's try to make some observations here. Observations, right? So the first observation is you will have to do at least one round, right? That's a very clear-cut observation. The number of rounds that you will have, will be at least 1. Why? Because in just one round you will be able to collect, like you have to do at least one round to collect all the numbers from 1, 2, 3, so on till n. What I'm saying is, guys, in the best case you could be given an array like this: 1, 2, 3, 4, 5, so on till n. So in just one round, you will collect all the guys in order. Important thing is you have to collect all the guys in order, right? Fine. So yeah, number of rounds is at least one. Now what? So this observation is there. What next? Next observation. So let's say you were trying to collect numbers like this. Let's say you were collecting 1. So you are given an array here, right? So let's say you are given an array like this: x1, x2, x3, so on, xn minus 1 and xn. So this array is given to you. Fine. Now let's say you are trying to collect the numbers. So in the first round, you are going from left to right like this. So first you found 1. Okay. Then let's say you found 2. Okay. Then let's say you found 3. But now you have reached the end of the array and you didn't find 4. Right. So if you didn't find 4, you will have to start a new round, right? Yeah, okay. So I'll start a new round here. Let's say then I again go from left to right and try to find 4. Okay. Then let's say I found 5. Then let's say I don't find 6. So maybe I found 4 somewhere here, 5 somewhere here, and then 6 is not after 4 and 5. Important, right? So 6 is not found after 4 and 5. Similarly here, in the first round, I first found 1, then 2, then 3, but 4 was not after 1, 2, 3. Okay, fine. So similarly, 6 was not found here. Okay, so maybe I can start one more round, like 6, 7, and maybe let's say it goes on and we find all the elements. But what is something that you observe here? See, in the first round, you found 1, 2, 3 in order, but 4 was not found. So it means 4 was either maybe somewhere here, or somewhere here. In a way, this guy was before 1, 2, and 3. Right? It was present somewhere before 1, 2, 3, right? Because when you were trying to collect numbers like 1, 2, 3, so on, 4 was somewhere here. That's why you missed it. Right? You missed 4, and that's why when you were trying to get 4, you were not able to find it because it was somewhere before. Right? So it could have be here in this position, or in this position. Right? Before. Okay, fine. Similarly here, you collected 4 and 5. But when you tried to look out for 6, it was not found on the right side of 4 and 5. So what does it mean? The 6 was somewhere before 5 or somewhere before 4, right? So 6 was somewhere here or somewhere here. Was before 4 and 5. Okay. But look about one thing here. Fine, 4 was before 1, 2, 3. 6 was before 4 and 5. Doesn't it mean that 4 was before 3? Right? Doesn't it mean 6 was before 5? Perfectly fine, right? So you had to start a new round because 4 was present somewhere before 3. Right? You agree with me there? You had to start a new round because 6 was present somewhere before 5. Makes sense? So what I'm saying is, when we go from 1 to n, if some x is found before x minus 1, that is this 4 was found before 3, the 6 was found before 5. Similarly, let's say let's say maybe 8 was found before 7, then you had to start a new round, right? So this makes sense, right? So when you go from 1 to n, if x is found before x minus 1, you have to start a new round. So using this observation, you can clearly write an approach. What you can do is, you know that number of rounds will be at least 1. So maybe you can initialize the rounds to 1. Then you can try collecting numbers. From 2 to n. Right? So you know that it means that you have collected 1 first. Right? So rounds is 1. It means you have started collecting from 1. So initially you have picked 1. Then we'll start collecting 2, 3, 4, so on till n. You can just write here, if position of x is less than position of x minus 1, that is this x is found before x minus 1. That is, if 4 is found before 3, that is 6 is found before 5, then of course I'll have to start a new round. This makes sense, right? So here, if this happens, then of course you can do round plus plus. And then this is done. In the end, you can just print the number of rounds. Very simple question, right? So, and you can do this here. Why? Because n was only as high as 1e5. So you can definitely run a loop from 1 to n, right? And about this position checks, you can maybe store it in the map or something. So in the worst case also, you will not consume more than n log n, right? So this is a perfectly fine approach. I'll go through it again. See, we know that there will be at least one round. Because in the worst case, like the best case, you can just collect numbers from 1 to n straight away. So rounds are at least one. Fine. Then you'll go from x equals to 2 till n. In other words, you'll try collecting elements 2, 3, 4, 5, 6, so on and so forth. But whenever whenever x is found before x minus 1, that is maybe 4 is found before 3, or maybe let's say 5 is found, or maybe let's say 6 is found before 5, you definitely know a new round will start. Make sense? So round plus plus. And in the end, you can just print the total number of rounds. Make sense? I guess it does. So what is the time complexity of this approach? See, initially you will have to calculate all the positions, right? So maybe while taking the input only, you will have to create a map which just maps the numbers 1 to n to their positions. So this will have to create. So there will be a map used here. So this will consume what? N log n for all the n elements, n insertions. So a single insertion costs log n in a map. And then again here, you are going through all the n elements here, order of n elements, and each one of them you are comparing, right? So again, these things are going to consume log n time. So again into log n. So overall time complexity here you can see n log n. Fine. Space complexity, you are storing n indices, so space complexity will be order of n again. And that's the approach, guys. So if you want dry run, I can do a dry run. Let's do this dry run very quickly on the example that was given to us. Let's say this was 4, 2, 1, 5, 3. So indexes were 1, 2, 3, 4, and 5. Okay, so we'll assume that we have a map which stores the positions of all the guys. Now we will go from, so we have initialized the rounds to 1. Now we'll go from start to end. So we'll start to end. So we'll start x equals to 2. So we have to collect numbers from 2, 3, 4, 5, right? So x will go from 2, 3, 4, 5. Okay, so let's start from 2 then. So is 2 coming before 1? Is 2 before 1? Yes, indeed. So definitely there will be one more round. So rounds will be incremented. Then let's go to 3. Is 3 before 2? No. So 2 and 3 will be collected in the same round. So rounds won't be incremented. Now 4. Is 4 before 3? Is 4 before 3? Yes. So 4 won't be collected in the same round as 3. So yeah, increment the round. There will be 3 rounds. Then come to 5. Is 5 before 4? No. So 4 and 5 will be collected in the same round. So fine. And in the end, we can just print out 3. So yeah, I mean that's about the pseudocode and the dry run. So I hope you have understood the explanation till now. If you did, please comment understood in the comment section of the video right now, and then we can look at the code. Okay guys, so here's the code. First things first, I'm taking n as input, which is the size of the array, or it defines that we have elements from 1 to n exactly once. Then here I'm creating the position map. So by taking the input itself, whenever I take the input, I'm just storing the position of that number, right? So notice I'm just using one based indexing. Whichever type of indexing you can use, it doesn't really change the question. Then we initialize the rounds to 1. That is, we pick 1 and the round begins. Round 1 begins. Now we go from I equals to 2 till n. That is, I'll try to collect elements from 2, 3, 4, so on till n. If the current guy x is found before x minus 1. Right, if position of I is less than position of I minus 1, then this guy won't be collected in the same round as I minus 1, right? If 4 is found before 3, then 4 won't be collected in the same round as 3. Fine. So we'll have to do a new round for that. So that's why round plus plus. And in the end, we can just print number of rounds. And time complexity, we already know n log n. Why? Because here for this loop, for storing the guys, n log n will be consumed. And here for checking, here for order of n guys, you are doing order of n. For order of n guys, all in all, total you are doing order of n checks. Each check costs log n. So that's fine log n. Space complexity, order of n for this map, because we're storing index for all the guys. And that's about the question, guys. So I hope you liked it. If you did, please give it a thumbs up. And I'd love to see if you can paste solutions in your programming language in the comment section of the video. I'll see you in the next one.